Hello there students. This question is from GATE 2007. It's a 4 marks question, 2 marks for each part. So we have 2 parts to this question. Let me read out the first part. Consider a machine with byte addressable main memory of 2 raised to the power 16 bytes. Assume that a direct mapped data cache consisting of 32 lines of 64 words each is used in the system. A 50 cross 50 2D array of bytes is stored in the main memory starting from memory location 1100H. Assuming that the data cache is initially empty, the complete array is accessed twice. Assume that the contents of the data cache do not change between the two accesses. How many data misses will occur in total? Okay. So first of all, let's find out the split for physical address. They are saying main memory is 2 raised to the power 16 bytes. Also, it is a byte addressable memory. So you can say we have 2 raised to the power 16 words in main memory because it's given one word is equal to 1 byte. That means physical address will be a 16-bit value. Okay, because we need to identify one word from total of 2 raised to the power 16 words using this physical address. So obviously it's going to be 16 bits. Also, they have told we are using a direct mapped cache. That means physical address will be split into 3 parts: tag, line number and block offset. Tag, line number, block offset. Let's find out how many bits will be the block offset. Cache has a total of 32 lines, 64 words each. That means block size is equal to line size is equal to 64 words. Okay. To identify one of 64 words, you need 6 bits. So this part is 6 bits. Okay. Block offset is used to identify one word from entire block. Block is 64 words. To identify one of these 64, we need 6 bits. Then cache has 32 lines. Obviously, line number field will be 5 bits. Okay, because to identify one line from a total of 32 lines, you need 5 bits. Then 5 plus 6 is 11. 16 minus 11 will be 5. Okay. So this is how we are splitting the physical address according to the question. 5 bits tag, 5 bits line number and 5 bits block offset. Now let's talk about the array they have mentioned in question. It's a 50 cross 50 2D array of bytes. The important point is it's an array of bytes. Also, we know one word is equal to 1 byte. That means we can say each element of this array is of one word. Okay, so each element in this array will occupy one address in the main memory or one word in the main memory. Obviously, one word is occupying one address. So you have a total of 50 cross 50. That means 2500. We have total 2500 words or bytes in this array. Saying this also means this array will consume 2500 addresses in main memory starting from the address 1100 in hexadecimal. Okay, let's see how many blocks of main memory will be used. So total we have 2500 words in the array and they are starting from address 1100H. Let's find out how many blocks will be used. One block is 64 words. We have total 2500 words. So number of blocks required to save the array. It will be total size of array in words by size of one block in words. Okay, so you can see we have total size of array is equal to 2500 words. Size of one block is 64 words. So 39.06 blocks will be required to save this array. Okay. Now, once you just try to bring even single word in the cache, you know entire block will be fetched. So this last block, even though it contains 0.06 part of this array only, okay. What I'm trying to say, the 40th, 39 blocks are filled completely. 40th block contains only a small part of the array. Even though it contains a small part of the array, still will fetch the entire block into the cache. So you can just assume there are 40 blocks which contain this array. Let's call these blocks block number 0 to block number 39. Okay, 0 to 39, they will be 40 in number. So these are the 40 blocks, each containing 64 words. And in total, there will be 2500 words of the array. That means block 0 will contain word number 0 to 63 of the array. Okay, out of 2500 words in the array, 0 to 63 will be saved in block 0. Similarly, this will contain 64 to 127. Okay. Similarly, from 128 onwards will be present in block number 2. Okay. Now let's see the starting address. Where will be it mapped in the cache? Starting address is 1100H. 1100H. That means binary equivalent will be 0001, 0001, 4 zeros and again 4 zeros. Okay. So I have converted this hexadecimal number into a binary number. It's actually an address of the main memory. Okay. They are saying array begins from this address. You also know that addresses of main memory are split in this way. That means 5, 5, 6. It's splitted into these fields. First field is 5 bits. That means this much. Okay, these are 5 bits. It will be the tag part. Second field is line number, which is also 5 bits. So we have 3, 4 and 5. 5 bits here. Okay. And then we will be left with 6 bits. So 4 plus 2, they are 6. Like this. Okay. Now you see, this address, the starting address of the array, it will be mapped onto which cache block or which cache line. Okay, that will be given by the line number field in this address. Line number field is 00100. That means 4. Okay, so it will be mapped onto the 4th line in cache. Whatever block this is in memory, that block, whenever we'll fetch it, we have to place it here. Okay, at this line number. I've represented the 32 lines of cache by these numbers. They have given cache as 32 lines. Maybe I just forgot to mention this in starting. So this is our cache. Now you see, each line has 64 words. So there will be 64 words in this line. Also, our block is 64 words. That means 0th element of array will be found here. 63rd element of array will be found here. This entire block contains 0 to 63 elements of array, which means total of 64 elements of the array. Okay. And similarly, block 1 will be mapped here, block 2, 3, 4, so on till maybe 26th or 27th block will be mapped here. Okay. Now let's see how are we accessing this array. We'll be accessing this array block by block. Let's assume that we are using row major representation of array. Also, we are accessing it row by row. Okay. That means the array will be accessed in this order, 0 to 63, then 64th word till 127th, so on. Okay. So we'll access it in increasing order only. That means block 0, block 1, block 2, so on till block 39. Also in the question they have given that it's accessed twice. That means from the first element of array to the last element of array, once it is accessed, then so on second time it is accessed. That means block 0 to block 39 one time, again from block 0 to block 39 second time. This is how we are accessing it. Now let's talk about the number of misses. When 0th word is accessed, okay, let's say initially our cache is empty, there's nothing in cache. When 0th word is accessed, cache is empty, certainly it will be a miss. Rather, for each of the block, whenever it is accessed for the first time, it will be a miss. Because first time access means it will not be present in the cache. That means there will be 40 misses for the first iteration. Let's see how. 0th word is accessed, it will be a miss. Now, because there is a miss in this block, this entire block will be fetched and placed into the cache. So here we have kept block number 0. 0th word was a miss. There is one miss for block 0. After that, second word, third word, fourth, fifth, sixth, so on till 63rd word. These will be hits. So there are 63 hits and only one miss for this block. Okay, so after accessing all these 63 words, we'll come to 64th word. Now 64th word, if it's present in the cache, it will be in the 5th line. Okay, 5th line or 5th block of cache is empty. That means there will be a miss while accessing 64th word. Now because there's a miss, we'll fetch the entire block. Even though we required to access 64th word, but we'll fetch the entire block only. So block number 1, which is actually the second block. If this is first, this is second. But we start counting from 0. So block number 1 will be brought into the cache and will be placed here. Now let's see which one will be the second, the next access. It will be to word number 65. It will be found in this block. In block 1 placed in line number 5 of cache. Then so on till 127, all of them will be a hit. Okay, so first miss was here, second miss was here. Now I think you have got the pattern. Then block number 2 will be accessed, block 3, block 4 and so on till block 39. So there will be one miss for every block. And if you just keep on counting, I think block number 27 will be placed here. Okay. So for all these 27 blocks, there will be 27 misses. After that, you will start from line number 0 of cache. So block number 28 will be placed here. block number 29, block number 30, block number 31. Okay, so 31st block will be placed here. After that, when you will try to access the 32nd block, what will happen? You will get to know that it has to be placed in 4th line of cache. Okay, but this one is already filled. So what you will do, you will replace this block 0 and it will be updated with block number 32. Okay. Similarly, all these will be replaced with blocks that will be following 32. So 33, B34, B35 and B36, B37, B38, B39. Okay, so all the 39 blocks are accessed. Whatever would have been present here will be replaced. Let me also write that. So B4 would be present here, B5, B6, B7. Okay. So when we were accessing it from the starting, we loaded B0 here, B1, B2, B3, B4, B5, B6, B7, B8, 9, 10, so on till B27. After that, we required B28. It will be mapped here. 29, 30, 31 till 32, till 31, they will be mapped to line number 3. Whenever you try to map block number 32, it will be mapped on this line number, line 4. So you have to replace whatever was present in this line. So on, you will just keep on replacing all these blocks from block number 0 to block number 7. Now, one thing is, there were 40 misses while accessing the array for the first time. I'm writing it here. So there were 40 misses while accessing the array for the first time. You don't even need to do such things to find it out. Okay, because all these blocks are accessed for the first time. There's no chance they will be present in the memory, okay, in the cache memory. So even though we don't need to do such things, it's very clear that all these 40 will have to be a miss. So why am I doing all this? Because we need to know for the second time, there's a possibility that some of the blocks might be present in the cache memory. So to know that which all accesses of these blocks will be a hit when we are going to access the array for the second time. For that purpose, I am doing these things. Okay. Now let's access it second time. After block number 31, you again start from block number 0, because after you have accessed the element number 2499, that is last element in array, you will come back to element number 0. Okay. So this element number 0 will not be present in the cache. Why? Because it is a part of block 0. Block 0 has already been replaced to accommodate block number 32. Okay. That means, okay, first thing, this block 0 has starting address 1100H. It will be again mapped to this line only. Okay. Then in this line, you'll get to know that block 32 is present by checking tag of this line. That means this block is not in cache. Certainly this is a miss. Okay. So after experiencing 40 misses, again we have a miss here. So you will replace it to again accommodate block number 0. Okay, this one block. So I think I'll have to erase all that and write it again. So I'll just speed up the video. Okay, so in all these blocks, we will be having, so block 10, block 11, block 12, block 13 will be here, B13 is present here, B14, 15, 16, 17, So B18 will be present here. 19, 20, 21, 22, 23, 4, 5, 6, 7. B27 will be present here. Okay. Now you know block 0 has been mapped here. That means you replace B32 and update with block 0 again. Then after accessing this word number 0, all these 63 words will be a hit. That means block 0 is finished. Then you will move on to accessing block 1. Okay. Block 1 will be mapped here. But in this cache line, we have block number 33. That means this one is a miss and you will update it with block 1. Okay. So on, you will experience a miss till here because none of these blocks, block 1, 2, 3, 4, 5, 6, 7, they are not present in the cache. That means all these will be again replaced. Okay. And you will bring block 2, block 3, block 4, block 5, block 6, block 7 into the cache. What has happened is you accessed the 0th, while accessing the array for second time, you tried to access 0th word. It was not there in the cache. You brought block 0. Then there will be 63 hits. Okay. Then for 64th word, there was a miss. One miss, you actually brought 64 words starting from address 64 to address 127. That means just for one miss, 64 words were brought into the cache. So next 63 accesses will be a hit. I'm actually repeating things again and again just to make you people memorize these things. Okay. It will be helpful in other questions also. If you just repeat these things again and again, they'll just be saved into your mind. Okay. So just bear with me. Now, when you access this block number 7, there was one miss for this block 7. Let's count how many misses have we encountered while accessing array for the second time. Block 0 to block 7 were a miss. That means there were 8 misses while we tried to access this array for the second time. Okay. Then let's see what happens when you try to access block 8. Block 8 is found in the cache. Okay. Block 9, 10, 11, 12, 13, 14, so on till block 27 will all be a hit. Okay. Now you see, you don't need to do anything for these hits. They will be found in cache. That's it. That means after block 7, you accessed all the blocks till 27, rather till 31, because they will also be a hit. Okay. Now, after this block number 31, you will not find block 32 in cache. Okay, because it was replaced. That means I am again short of space. Okay, anyways, this one will be deleted and you will bring block number 32 here. Okay, so this one will be updated with block number 32. I'm using another color and I'm just writing it here only. So this one will be replaced with block number 32. Okay, B32. Again, we have a miss. Okay, here also you will be having a miss. One more miss, so on till B7. Okay, you will be having misses. You will bring block number 32 here, 33 here, 34, 35, 36, 37, 38, 39. And all these will be replaced. Okay, with blocks from 32 to 39. That means there will be 8 more misses. Okay, plus 8. This is your answer. So you have accessed till block number 39 in line number 11 of the cache. Okay, that means the array is accessed twice. These are the misses that you experienced. First time every block was a miss. That means 40 misses. Second time there were only 16 misses. Okay. 8 these and 8 these. So 16 misses for the second time. Now let's calculate how many misses are there in total. So 48 plus 8 is 56. Answer to this question is 56 misses. Okay. Now I'll just read out the second part and we'll solve it. Part 2 says, which of the following lines of data cache will be replaced by new blocks in accessing the array for the second time? Okay. See, they are saying out of these cache lines 0 to 31, which all will be replaced when you are accessing array for the second time. It's very clear. Line number 4 to line number 11. Only these lines are where we updated something. Okay. So 4 to 11 is your answer to the B part. Now, this question was worth attempting because it had these 2 marks for free. Okay, so the camera batteries just died. Anyways, I've charged them and let's continue. So I was saying, second part was a cakewalk. No, once you have solved this first part, you already know the answer to the second part. So it was actually only one question for 4 marks. Okay. Second part was just there to maybe make you scared that this might be a lengthy question. So it was worth attempting even in the real exam. And you won't take this much time. I've explained you and I was going really slow. Once you know the split and the number of blocks, you'll just map it in like one go. Just 10 seconds for this stuff. So calculating answer 56 is simple. Okay. But there's a lot that you need to know in advance. Here we were learning the concept. In real exam, you know the concept, you just need to implement it. Okay. So next thing that I need to mention is, when I teach such questions in offline classes, students come up with replacement policies. One student had this question, why are we not using like something like optimal or LRU? Just see, this is a direct mapped cache. You don't even need to worry about replacement policies because there's no choice. It is a direct mapped cache. In direct mapping, you know exactly where that block will be placed. You don't have a choice. Replacement policies are used only when we have a choice. Like there are these 4 places where it can be loaded. So you just use the replacement policies like which block will be replaced. Here you don't have any choice. This block number 32 gets mapped here only. Whatever was present in this line number 4 will certainly be replaced. Now you have only one option. Why to use any algorithm to determine with what to replace? Okay. And also they haven't mentioned about anything about how we save this array. Just assume it's saved in row major. That's the default setting. Even in C language, we use row major. I've discussed in theory lectures of C language multiple times. So it's used in row major. Also assume it's accessed in row major. Okay. Now, what I'll be doing is, I'll record this video in Hindi also. After that, I'll again record this video and solve this question in some other way. The other way, okay. I'll follow the concept of groups there. You'll get even more insights if you watch that video. But I'll not just connect both of these videos because already this video is like around half an hour. Okay, thank you very much. Okay, so I actually forgot to discuss one point while providing the solution to this question. The thing is, how are you very sure that 1100H, that this address will be the 0th address of some block? How can we say that element 0, whose address is 1100H, will be the beginning word of some block? Okay, that means possibly 1100H could fall in middle of some block. If it falls in middle of some block, that also means element 0 of our array will be in middle of some block. That also means that 0 to 63, these elements could not be accommodated in that block. Some of the last elements would just move to second block. Okay, so how do we know that some block would begin from this address? Answer to this question is these block offset field bits corresponding to this address. This address says that block offset is 0. Okay, that means in some block of main memory, this one is the 0th word. That means that particular block begins from this address 1100H. Okay, and which block are we talking about? It will be this block. These two fields combinedly will give you the block number in main memory whose first word, rather 0th word, is 1100H. Okay, now this will be some block. It is 1000100. This block number will be having its 0th word as 1100H. But this block number, whatever it converts to in decimal, we are calling this one as B0. Okay, and so on. These are not the blocks of main memory. We are just naming some random blocks of main memory, a continuous stretch. We are renaming them to from B0 to B39. Actually, they'll have some number. Obviously, how can this block 0 of main memory contain address 1100? It would begin from address 0, na? So this ones, they are just names given by me. Okay.